In this video, we are going to talk about comparison tests. So far we've talked about different types of series. We've talked about geometric series, telescoping series, harmonic series, and then some series that are going to be a little bit difficult to kind of identify. But we know that if we are able to narrow it down to a p-series or maybe a function that you can go ahead and integrate, we can use the integral test. So we've dealt with a lot of different types of functions. Or a lot of series. So one of the things that we want to be able to do is that if we have a series, maybe n goes from 1 to infinity, of 1 over 2 to the n plus 1. Okay, so if we have this particular series and we take a look at it, you kind of look at it and say, okay, well, it doesn't look like a p-series because a p-series should be n to the power of some power. And then if you try to do the integral test, I don't think that would be a really good idea, because if you try to take the integral of this will be horrific to do. But one of the things that it does look like, it looks like a geometric series. Okay, so maybe this looks like the sum from n goes from 1 to infinity of 1 over 2 to the n. So this thing right here, this series looks a lot like this series. And I know that this series converges by geometric series. So that's what I know. Why? Because we know here that r is going to be equal to 1/2. If I were to go ahead and change this up like we've done before, we know that r is equal to 1/2, which is less than 1, so therefore it converges. So if we know that this guy converges, what can we say about this guy? Okay, well, one of the things to kind of know is that adding a term in the denominator, so if I were to add a number in the denominator, the whole fraction is going to get smaller. Okay, if I subtract a term on the bottom, that's going to make the whole fraction bigger. Okay, so what in this case, what you can look at, if you look at this 1 over 2 to the n plus 1, you can see that this is going to be smaller than 1 over 2 to the n. Okay, and that's because I added a 1 on the denominator, which makes this whole fraction much smaller. Okay, so if this thing converges, okay, if something bigger converges, then that must mean that this also converges. And that is the whole point of the comparison test. You want to be able to compare this particular term or this series with something else that kind of looks like it. So let me go ahead and explain a little bit of what exactly the comparison test does and how is it going to be useful. Okay, now trying to come up with some sort of series isn't going to be easy, but it will give you a little bit of a hope, and it can greatly simplify a lot of the math. So this is basically what it is. So suppose that some series, sum of a sub n and sum of b sub n are series with positive terms. Okay, so this is what you can say. So if b sub n, okay, the sum of b sub n is convergent and a sub n is smaller than or equal to b sub n for all n, then the sum of a sub n is also convergent. Okay, so basically, if you can come up with some other series, okay, and you can show that this series that you chose is less than that, and if we know that this b sub n is convergent, then the sum of a sub n is also going to be convergent. Okay, which is basically what we said here. We chose a function or a series that is much bigger than this guy. So if I know that this guy converges, then this guy is also going to converge. Okay, and then here's the second statement. So if the sum of b sub n's is divergent, so let's say, for example, this guy diverges, and a sub n is greater than or equal to b sub n for all n, then the sum of a sub n is also divergent. Okay, so if I can think of a series that's much or that's a little smaller than a sub n, and I know that this small thing is divergent, then obviously this series is going to also be divergent. Okay, so that's basically the goal of it. So keep in mind that adding a number on the denominator will make the fraction bigger. I'm sorry, make the fraction smaller. And subtracting a number, the denominator is going to make it bigger. Okay, so it's kind of the opposite of what would happen. Okay, so one of the things that are that you might be wondering is like, okay, what are some good things to kind of compare? So what series are good to compare? Okay, now you can go crazy with these, but typically one of the things that the ones that are really safe is like you want to compare it to maybe P series, and you want to compare it maybe with geometric series. Okay, or maybe even telescoping or harmonic, but usually P series are pretty good. This is something that I would really recommend. There's some problems that where you might want to compare a function to something else, and then you might have to use the integral test. But these are really good to kind of compare with. So let's just do a couple problems so that we can kind of get a taste of what this really looks like. So determine if the series converges or diverges. Okay, so let's say you have the sum from n goes from 1 to infinity of 5 over 2n squared plus 4n plus 3. Okay, so let's say we have something that looks like that. Okay, so first of all, when you look at the series, this definitely doesn't look like a telescoping series or a geometric series. It doesn't look like any of that stuff. You definitely don't want to use the integral test here because if you look at the denominator, it looks like you might have to do a partial fraction decomposition. So maybe that might not work, or it might be a little tedious. But it looks kind of like a P series. You know, you have an n squared on the bottom. Okay, so what can you do? Well, can we probably compare this with something else? Well, we know that P series kind of they converge if P is greater than 1. So can we possibly show or compare this to a P series? Well, we know that 5 over 2n squared plus 4n plus 3. Notice that there's a whole bunch of terms that are being added to this. So this thing is going to get smaller and smaller, this whole fraction. Okay, so we're going to try to compare it with something else. Okay, so we're going to compare it with, we're going to keep the 5 on the bottom, on the top, okay, because the 5 isn't really going to do anything, but I'm going to compare it to 2n squared. And the reason why is because you can see that this particular term is going to be way bigger than this guy, because in the bottom you're just adding additional terms, so it's making the bottom part bigger, which makes the whole fraction smaller. Okay, so this is a true statement, and you can plug in a value of n, and you can see that this guy is always going to be bigger than this guy. Okay, so now what I'm going to do is I'm going to work with this particular term. Okay, so I'm going to look at the series summation from n goes from 1 to infinity of 5 over 2n squared. I can take out the 5 halves, and I get the sum from n goes from 1 to infinity of 1 over n squared. This guy right here converges by P series. Oops, that's not how I spell series. So this converges by P series since P is greater than 1. Okay, P in this case is equal to 2, which is greater than 1. Okay, so if this guy converges, what does that tell me about my original sequence? Or, well, this thing will be a sequence and then the whole series. Well, that means that this whole series is also going to converge. Because remember that we said that if we can find some series, okay, B sub n, such that it's less than A sub n, or is greater than a sub n, and I know that this guy is convergent, then that means that my original problem is also convergent. So because this one converges by p-series, by comparison test, the sum from n goes from 1 to infinity of 5 over 2n squared plus 4n plus 3 converges. Okay? All right, let's do another problem. Okay, so let's say that was part A. So this is going to be part B. So let's say we have the sum from n goes from 1 to infinity of n over n squared minus cosine squared of n. Okay. Now, one thing that you might want to look at and one thing that you might want to take into consideration is you can basically look at the highest terms if you really want to, okay? So notice that you definitely don't want to use the integral test here. That would be terrible, okay? So one thing that you can do is you can try to compare n over n squared minus cosine squared of n with the powers of the highest terms, okay? Which in this case will be n over n squared. Now you have to think about this. Is this term going to be greater than or is it going to be less than? Okay, well notice in the bottom portion, you're being subtracted. Okay, when you subtract something on the denominator, okay, it's going to get smaller, so the whole fraction is going to get bigger. So this whole thing is larger than that. Okay? Okay. All right, and notice that this thing is always going to be a positive number because it's being squared, so you're always going to be subtracting some particular term. Okay, now this n over n squared is just going to be 1 over n if I were to go ahead and rewrite that. Okay, so you have that n over n squared minus cosine squared of n is greater than 1 over n. Now, what do we know about the sum of 1 over n? Well, this guy is a harmonic series. This diverges. So if this guy diverges, which is much smaller than that, then that definitely diverges as well. Okay, so this diverges by harmonic series. Or you can say p series as well, or p series. Okay, so by comparison test, okay, the sum from n goes from 1 to infinity of n over n squared minus cosine squared of n diverges. Okay, so this guy is going to diverge, and that's basically from number 2. So number 2 said that if you find some sort of series that's divergent and it's smaller than a sub n, okay, because we proved that this new series is smaller, we can see that it's less than this term, then what you can say is that this new term, or the old problem, is going to also be divergent, which in this case it is. Okay. All right, let's do one more problem. So let's say we had the sum from n goes from 0 to infinity of 2 to the power of n sine squared 5n divided by 4 to the n plus cosine squared n. Okay. Now let's go ahead and figure this out. So we're gonna start off by looking at this inside part, the thing inside the series. So 2 to the n sine squared 5n divided by 4 over n plus cosine squared of n. Okay. Now you can all look at the main coefficients 2 over n, 2 to the n over 4 to the n. You can kind of look at that, but we have to make sure that this is this is worth it, because you can see that the biggest number that sine squared n, 5n, can be is just 1. Okay, that's the highest number, because if I plug in any angle in here, it's just going to be squared, and the highest one is going to be 1. Okay, and then this bottom part, when you're adding something to it, okay, when you add something to it, you're going to make it smaller. Okay, you're going to make this bigger and make the whole thing smaller. So this is going to be less than that. Okay. All right. So now what we have to do is deal with this guy. So, okay. So this guy is going to be 2 over n, which is just 2 over 4 to the n power, which is equal to 1/2 to the nth power. Okay. So all we have to see is, does this converge? Well, it does, right? Because the sum from n goes from 0 to infinity of 1/2 to the n. Well, this is just a geometric series. Okay. So, and then since r in this case equals 1/2, which is less than 1, then it converges. Okay, so if this guy right here converges and you see that this whole thing is less than that, then that means that this guy should also converge. So by comparison tests, the sum from n goes from 0 to infinity of 2 to the n sine squared 5n divided by 4n to the n plus cosine squared of n converges as well. Okay, so with these comparison tests, honestly, it's not easy. It takes a little bit of practice, and you have to be able to bounce. And you can, in the next video, you'll see that this doesn't always work. So are there other alternatives that we should use? And there is something else that we can use, and I'll show you what that is in the next video.